Okay, welcome to video number 2 for 6 things to know for getting a band 6 in the HSC for advanced maths. Video 2 is focusing on another massive part of any paper, exponential growth and decay. So I thought I'd start by just introducing you to some things that are important to know for any exponential growth and decay question. First things first, and this is just for the entire applications calculus to the physical world topic, but just knowing initially is at time is 0. Very, very common question. Second thing to know is our applications of calculus questions on exponential growth and decay are always in the form of P equals AE to the KT. That's something growing exponentially, and if it was decaying, it would just have a negative k. Now they can use different values here, but P usually stands for the population, A is your initial population, E is just Euler's number, K is some sort of rate, and T is for time. An important thing to know, which comes up here and there in HSCs, is being able to prove they commonly say prove something to do with this. But basically it's just about knowing how to differentiate. Think about differentiating exponentials. If you had the exponential y equals 2e to the 2x, we differentiate the power and times it out the front. So y dash in that case would be 2e to the 2x, and we don't subtract 1 from the power. So now think of it differentiating P with respect to T. Don't be confused. Think about, okay, we're differentiating with respect to time, so I'm going to differentiate the power and times that out the front. So I'm going to have the derivative will be K, and it's timesing with AE to the KT. Now, it's just a matter of saying, well, I know that P is equal to AE to the KT, which is what I have here. So that's how then we can say, so therefore, dP on dt is equal to K timesing by P. It's just a common proof to know how to get it into that form, and it's just knowing your derivative. Okay, one other thing in these questions when it comes up about rates of change, this is the derivative. So as soon as you see the word rate of change, differentiate with respect to whatever you're doing. It's usually with respect to time. So drill that into your mind. As soon as you see the word rate, differentiate. Rate, differentiate. Say it to yourself 7 times and you won't forget it. Rate, differentiate. Rate, differentiate. Okay. And lastly, I just wanted to talk about A, K, T, and P, our values here. The idea is with all exponential growth and decay questions, it's just about an equation. They'll give you every letter except one, and you're just rearranging for that missing letter. What I will note is A being our initial population and K being the rate. These don't change. Now, when I say that is unless said otherwise. So once you've found the initial population, and once you've found the rate that this population is exponentially growing or decaying, those values don't change for the rest of the question unless they say otherwise, which is uncommon. However, T and P, these are the values that are changing depending on what time will give you a certain population. So these do change. So it's just about understanding that once you've found A and K, the values, they don't change. You can use them and you can carry them through for other questions. But T and P, they're going to change each question depending on what you need to find. So what I have here is a pretty basic question so far, just a past HSC question on something exponentially growing. It's bacteria. And I just thought we'd run through this, and then I'll show you a more complicated version. So understand the question initially. Don't rush into part 1. Understand what the question's saying. So here is our formula. Oops. We have to show that K is this value to 4 decimal places, and it tells us that after 20 minutes there are 2,000 bacteria. So instead of P for the population, they're using N for the number of bacteria. Because I don't like words, I like numbers, I'm just going to tell myself straight away, okay, so when N is 2,000, T equals 20. So it's like a point, in other words, I guess, a piece of information in numbers now. And once again, like I said, all exponential growth and decay questions are just about, they'll give you every letter except one and you rearrange for that one. So now let's sub it in. So I'm going to have that so it's going to look like this once you've subbed it in, and now it's just about rearranging, okay? I have a power of K, which things that I'm thinking about at the moment is, okay, to undo a power, eventually I'm going to have to log something because that's undoing an exponential. When I rearrange, I'm going to have something that's going to look like this when it's simplified down. Now is the point where I'm going to undo my exponential. So to undo an exponential, we log both sides, okay? Now, I teach my class to log both sides. Some people may say write it in the form of a log. So if we log both sides, I'm going to have the log of 2 is equal to the log of e to the 20k. And this is where we say, okay, now log laws say that if we have a power, it can come out the front. So I'm going to then have log 2 is equal to 20k timesing by ln e. And I know that log of e is just 1. And why do I know that? Because that's really log e of e, which is just a log law that tells us that that is equal to 1. So rearranging, I'm just going to have, which gives us our value to 4 decimal places. So once again, an exponential growth and decay question is going to give you every letter except one, and you're just going to rearrange for that. So now look at part 2. It says, what is the rate, how many bacteria are there when t equals 20? So now I need to know the number of bacteria and t equals 20. Now notice before, I said once you find k, that sticks. You can use that for the rest of the question unless they've said otherwise. So I know, once again, subbing everything I need in, I'm going to have and my k value was when t is 120, and I sub that in, yes, I get 64,328. And questions like these, it's a good idea to put a therefore statement. So therefore, after 120 minutes, there are 64,328 bacteria. Okay, part 3. What is the rate of change of the number of bacteria per minute at t equals 120? Straight away, rate of change, rate, differentiate. So I have to differentiate my equation, and once again, I can use my k value that I already found further on. And I get dn of dt. Once again, differentiate the power and times it out the front. So 0.0347 is my derivative, timesing that by 1000 e to the 0.0347t. Which, cleaning up, I'm just going to jump 1, 2, 3, so 34.7 e So that's my derivative. That's my rate that this bacteria is changing for any value of time. It's now that I will sub in my value of time being t equals 120. So subbing it in and cleaning it up, I get that after 120 minutes, the rate of change in bacteria is 2,232, and that would be bacteria per minute. So notice that I see in the word rate of change, I differentiate, and then I sub in the value. Okay, and the last part, how long does it take for the number of bacteria to increase from 1,000 to 100,000? Once again, straight away I'm going to think, okay, what are they giving me and what do I need to find? What letter is missing? The key word there is how long, which means I'm finding time. So I need to find t when my population jumps up to, n is my population, 100,000. And once again, subbing it in, rearranging for the missing term. Things that I'm thinking about when I sub it in is, once again, I have a power that I need to find, which means somewhere along the lines I'm going to have to undo the exponential by logging. So there it is. I am dividing by 1,000, which leaves me with just 100e to the power there. And that's when I can then log. Once everything is gone, apart from just your exponential, that's when you can log both sides. The power comes down and times us, the log e becomes 1, rearrange, and I get t is equal to 132.7. Think back, what is the question asking again? How long does it take for the bacteria to increase from that to that? So then I would, therefore, the bacteria will take 133 minutes to reach a population of 100,000. Okay, so hopefully you can see now this repetition of the idea that they give you every letter except one, and it's just a matter of rearranging for that letter. What I want to do now is look at one slightly higher. So if you'd like to pause the video, give it a go using what we've just done, see what you can do, and then look back on the video once you have completed. Okay, so we are given the population model for a species of birds, and they're decaying because of that negative power. The first question wants us to find out how many birds there were when the observation began. So think about that. When something begins, that's at time is 0. So that's all it is. Another way of saying that is how many birds were there initially. So just so knowing that that's when I'm going to sub in time is 0. Remembering that anything with a power of 0 becomes 1 is the big mistake here that people can easily make. So knowing that gives you a value of 450. And once again, worded question, worded answer. So therefore there were initially 450 birds. Question 2. According to this model, what will the rate of change in the bird population be after 10 years? So straight away, rate, differentiate. Now don't look at something like that and get scared of how to differentiate it. It's just an exponential. How do we differentiate exponentials? Well, straight away this constant of 150 is going to drop away. To differentiate the exponential, I differentiate the power and times it out the front. The derivative of the power is going to be negative 0.03, and it's timesing by 300 e. 0.05, it looks like a 3, to the negative 0.03 t. And then just simplify. 0.05, that is. So once I've differentiated, then I sub in the value at t equals 10 they wanted. Now, they didn't say to any certain decimal places, which means usually you can leave it in exact form. I could even rewrite this as 60 over the square root of e, because it's power of negative a half. But either of them would be fine. Okay, part 3. What does the model predict will be the limiting value of the bird population? The limiting value of the bird population. Interesting question. So really here we're talking about what's the limit that this species will only ever reach. Okay, there's some sort of value obviously that it's going to approach. There's 2 ways to do this. Method 1 is thinking about as t goes to infinity, and method 2 you could draw the graph and visualize it. I'm going to show you both ways. The first thing I'll do is I will draw the graph. Thinking about how to draw this graph. Now in video number 3, so the next video, we will go into a bit more detail about exponential graphs. So I won't go into too much detail now, as I will cover this question or this type of question there. But if I'm drawing this exponential graph, it's going to look something like that. So it is negative gradient because it is decaying. It passes through 300, but then it gets shifted up 150. So therefore it's going to pass through here at 450 with an asymptote at 150, which I can clearly see that the limiting value of this is just going to be 150. The population, it's going to have a limit at 150. In fact, it'll never actually reach 150, but it's going to infinitely get very, 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 very close to it. However, another way I could have thought about this is thinking about just the equation of my population. The equation of my population is this. Which, the way I'd think about that is cleaning it up brings the negative power underneath and becomes a positive power. Now, imagine for large values of t, so as t goes towards infinity. So I'm subbing in huge values of t. Now, it's going to be timesing by this small number, but it doesn't matter because I'm going to be getting bigger and bigger numbers even though it's timesing by this small number. The bigger value of t, the bigger the power is going to be. So then the bigger the denominator itself is going to be. So this denominator is getting bigger and bigger and bigger, which means this fraction as a whole, 300 over that, the bigger the denominator, the smaller that fraction is going to be. So as t goes to infinity, 300 over e to the power of 0.05t is going towards 0. So therefore, if that entire thing is going towards 0, then the population is going to head towards 150 plus 0, which is just 150. Depends what type of learner you are. If you're a more algebraic style learner, maybe that is the better way to go. But if you visualize things and you like to understand the process in a visual way, the graph might be your best bet. Okay, and last question. The species will become eligible for inclusion in the endangered species list when the population falls below 200. When does the model predict this would occur? So for a bit more understanding, we want to know, well, 200 is going to be around here somewhere. So we want to know at what time does that occur. And that's when it's going to be eligible for this endangered species. So once again, it's giving us everything except one missing letter. They want to know when something happens, which means we're solving for t. We want to know what time. We want to know what time the population falls below 200. So I'm going to find out, well, what time does it hit 200? And then I'll know that it's everything after that. So it's just a matter of solving this equation here. piece by piece, bring everything over. Once again, I'm going to have to undo an exponential, so logs are going to be involved. So solving that and simplifying it down, you get a t value of 35.83, so therefore after 35.8 years will be your answer. Okay, and one thing I did just notice, which you would have already picked up, 0.05 times 300 up here is the number 15, not the number 60. So that was just a mistake, which hopefully you realised I made already. Okay, so there is our exponential growth and decay wrapped up. Hopefully you can start to see, like I said, those similarities in each question. It's just a matter of them giving you everything but one letter and rearranging, usually involving logs. Those important things are just knowing your graphs, rate, differentiate, and know how to solve for a power.